A complex number is a number that can be expressed in the form a plus b, where a and b are real numbers, and I is a solution of the equation x2 equals -1. Because no real number satisfies this equation, I is called an imaginary number. For the complex number a plus b, a is called the real part, and b is called the imaginary part. Despite the historical nomenclature, imaginary, complex numbers are regarded in the mathematical sciences as just as real as the real numbers, and are fundamental in many aspects of the scientific description of the natural world. Complex numbers allow solutions to certain equations that have no solutions in real numbers. For example, the equation x plus 1 2 equals minus 9 display style x plus 1 caret 2 equals minus 9 has no real solution, since the square of a real number cannot be negative. Complex numbers provide a solution to this problem. The idea is to extend the real numbers with an indeterminate I, sometimes called the imaginary unit, that is taken to satisfy the relation I2. Topic -1, so that solutions to equations like the preceding one can be found. In this case the solutions are -1 plus 3i and -1 minus 3i, as can be verified using the fact that I2 -1 minus 1 plus 3 I plus 1 2 equals 3 I 2 equals 3 2 I 2 equals 9 minus 1 equals minus 9. Display style -1 plus 3i plus 1 caret 2 equals 3i caret 2 equals left 3 caret 2 right left I caret 2 right equals 9 minus 1 equals minus 9 minus 1 minus 3 I plus 1 2 equals minus 3 I 2 equals minus 3 2 I 2 equals 9 minus 1 equals minus 9. Display style -1 3i plus 1 caret 2 equals 3i caret 2 equals minus 3 caret 2 left I caret 2 right equals 9 minus 1 equals minus 9. According to the fundamental theorem of algebra, all polynomial equations with real or complex coefficients in a single variable have a solution in complex numbers. Formally, the complex number system can be defined as the algebraic extension of the ordinary real numbers by an imaginary number I. This means that complex numbers can be added, subtracted, and multiplied, as polynomials in the variable I, with the rule I2 equals -1 imposed. Furthermore, complex numbers can also be divided by non-zero complex numbers. Overall, the complex number system is a field. The complex numbers give rise to the fundamental theorem of algebra. Every non-constant polynomial equation with complex coefficients has a complex solution. This property is true of the complex numbers, but not the reals. The 16th-century Italian mathematician Girolamo Cardano is credited with introducing complex numbers in his attempts to find solutions to cubic equations. Geometrically, complex numbers extend the concept of the one-dimensional number line to the two-dimensional complex plane by using the horizontal axis for the real part and the vertical axis for the imaginary part. The complex number a plus b can be identified with the point a, b in the complex plane. A complex number whose real part is 0 is said to be purely imaginary. The points for these numbers lie on the vertical axis of the complex plane. A complex number whose imaginary part is 0 can be viewed as a real number, its point lies on the horizontal axis of the complex plane. Complex numbers can also be represented in polar form, which associates each complex number with its distance from the origin, its magnitude, and with a particular angle known as the argument of this complex number. Definition. Based on the concept of real numbers, a complex number is a number of the form a plus b, where a and b are real numbers and I is an indeterminate satisfying I too. -1. For example, 2 plus 3i is a complex number. This way, a complex number is defined as a polynomial with real coefficients in the single indeterminate I, for which the relation I2 plus 1 0 is imposed. Based on this definition, complex numbers can be added and multiplied, using the addition and multiplication for polynomials. The relation I2 plus 1 0 induces the equalities I4k 1, I4k plus 1 I4k plus 2 -1, and I4k plus 3 equals I, which hold for all integers k. These allow the reduction of any polynomial that results from the addition and multiplication of complex numbers to a linear polynomial in I, again of the form a plus b with real coefficients a, b. The real number a is called the real part of the complex number a plus b, the real number b is called its imaginary part. To emphasize, the imaginary part does not include a factor I and b, not b, is the imaginary part. Formally, the complex numbers are defined as the quotient ring of the polynomial ring in the indeterminate I, by the ideal generated by the polynomial I2 plus 1 see below. Notation. A real number A can be regarded as a complex number A plus 0 I whose imaginary part is 0. A purely imaginary number b is a complex number 0 plus b whose real part is 0. As with polynomials, it is common to write A for a plus 0 I and b for 0 plus b. Moreover, when the imaginary part is negative, i.e. b -b, -4, 3-4 I can be written instead of 3 plus -4 I. Since in polynomials with real coefficients the multiplication of the indeterminate I and a real is commutative, the polynomial a plus b may be written as a plus ib. This is often expedient for imaginary parts denoted by expressions, e.g., when b is a radical, the real part of a complex number z is denoted by re z or z, the imaginary part of a complex number z is denoted by im z or z. For example, re 2 plus 3i equals 2 display style operator name re 2 plus 3i equals 2 quad and im 2 plus 3i equals 3. Display style quad operator name im 2 plus 3i equals 3. The set of all complex numbers is denoted by c display style math BF c upright bold or c display style math B c blackboard bold. In some disciplines, in particular electromagnetism and electrical engineering, J is used instead of I since I is frequently used to represent electric current. In these cases complex numbers are written as a plus bj or a plus jb. Visualization. A complex number z can thus be identified with an ordered pair re z, im z of real numbers, which in turn may be interpreted as coordinates of a point in a two-dimensional space. The most immediate space is the Euclidean plane with suitable coordinates, which is then called complex plane or Argand diagram, named after Jean Robert Argand. Another prominent space on which the coordinates may be projected is the two-dimensional surface of a sphere, which is then called Riemann sphere. Cartesian complex plane. The definition of the complex numbers involving two arbitrary real values immediately suggests the use of Cartesian coordinates in the complex plane. The horizontal real axis is generally used to display the real part with increasing values to the right, and the imaginary part marks the vertical imaginary axis, increasing values upwards. A charted number may be either viewed as the coordinatized point, or as a position vector from the origin to this point. The coordinate values of a complex number z are said to give its Cartesian, rectangular, or algebraic form. Notably, the operations of addition and multiplication take on a very natural geometric character when complex numbers are viewed as position vectors. Addition corresponds to vector addition, while multiplication, see below, corresponds to multiplying their magnitudes and adding the angles they make with the real axis. Viewed in this way, the multiplication of a complex number by I corresponds to rotating the position vector counterclockwise by a quarter turn 90 degrees about the origin. A plus b I equals a I plus b I 2 equals minus b plus a I. Display style a plus by c dot I equals I plus b I caret 2 equals b plus I. Topic: Polar complex plane. Topic: Modulus and argument. An alternative option for coordinates in the complex plane is the polar coordinate system that uses the distance of the point z from the origin O, and the angle subtended between the positive real axis and the line segment Oz in a counterclockwise sense. This leads to the polar form of complex numbers. The absolute value or modulus or magnitude of a complex number z equals x plus y is r equals z equals x 2 plus y 2. Display style r equals z equals sqrt x caret 2 plus y caret 2. If z is a real number, that is, if y 0, then r x, that is, the absolute value of a real number equals its absolute value as a complex number. By Pythagoras' theorem, the absolute value of complex number is the distance to the origin of the point representing the complex number in the complex plane. The argument of z in many applications referred to as the phase phi is the angle of the radius Oz with the positive real axis, and is written as arg z arg z. As with the modulus, the argument can be found from the rectangular form x plus y I x plus y, by applying the inverse tangent to the quotient of imaginary by real parts. By using a half-angle identity, a single branch of the arctan suffices to cover the range of the arg function, minus pi, and avoids a more subtle case-by-case analysis. Phi equals arg x plus yi equals 2 arctan y x 2 plus y 2 plus x if x greater than 0 or y does not equal 0, pi if x 0 and y equals 0. Undefined if x equals 0 and y equals 0. Display style varphi equals arg x plus y equals begin cases 2 arctan biggle frac y sqrt x caret 2 plus y caret 2 plus x bigger and text if x greater than 0 text or y neq 0 pi and text if x normally, as given above. The principal value in the interval minus pi is chosen. Values in the range 0 2 pi are obtained by adding 2 pi if the value is negative. The value of phi is expressed in radians in this article. It can increase by any integer multiple of 2 pi and still give the same angle, viewed as subtended by the rays of the positive real axis and from the origin through z. Hence, the arg function is sometimes considered as multivalued. The polar angle for the complex number 0 is indeterminate, but arbitrary choice of the angle 0 is common. The value of phi equals the result of aton 2. Phi equals aton 2 im z re z. Display style varphi equals operator name aton 2 left operator name im z operator name re z right. Together, r and phi give another way of representing complex numbers, the polar form, as the combination of modulus and argument fully specify the position of a point on the plane. Recovering the original rectangular co-ordinates from the polar form is done by the formula called trigonometric form z equals r cos phi plus I sin phi. Display style z equals r cos var phi plus I sin var phi. Using Euler's formula, this can be written as z equals r e I phi. Display style z equals re caret I var phi. Using the cis function, this is sometimes abbreviated to z equals r cis phi. Display style z equals r operator name cis var phi. In angle notation, often used in electronics to represent a phasor with amplitude r and phase phi, it is written as z equals r phi. Display style z equals r angle var phi. Topic: Complex graphs. When visualizing complex functions, both a complex input and output are needed. Because each complex number is represented in 2 dimensions, visually graphing a complex function would require the perception of a 4-dimensional space, which is possible only in projections. Because of this, other ways of visualizing complex functions have been designed. In domain coloring, the output dimensions are represented by color and brightness, respectively. Each point in the complex plane as domain is ornated, typically with color representing the argument of the complex number, and brightness representing the magnitude. Dark spots mark moduli near zero, brighter spots are farther away from the origin. The gradation may be discontinuous, but is assumed as monotonous. The colors often vary in steps of pi, 3 for 0 to 2 pi, from red, yellow, green, cyan, blue, to magenta. These plots are called color wheel graphs. This provides a simple way to visualize the functions without losing information. The picture shows zeros for plus or minus 1, 2 plus I, and poles at plus or minus square root minus 2I. Riemann surfaces are another way to visualize complex functions. Riemann surfaces can be thought of as deformations of the complex plane. While the horizontal axes represent the real and imaginary inputs, the single vertical axis only represents either the real or imaginary output. However, Riemann surfaces are built in such a way that rotating them 180 degrees shows the imaginary output, and vice versa. Unlike domain coloring, Riemann surfaces can represent multivalued functions like z _sqrt z. History in brief. Main section: History. The solution in radicals without trigonometric functions of a general cubic equation contains the square roots of negative numbers when all 3 roots are real numbers, a situation that cannot be rectified by factoring aided by the rational root test if the cubic is irreducible, the so-called casus irreducibilis. This conundrum led Italian mathematician Girolamo Cardano to conceive of complex numbers in around 1545, though his understanding was rudimentary. Work on the problem of general polynomials ultimately led to the fundamental theorem of algebra, which shows that with complex numbers, a solution exists to every polynomial equation of degree 1 or higher. Complex numbers thus form an algebraically closed field, where any polynomial equation has a root. Many mathematicians contributed to the full development of complex numbers. The rules for addition, subtraction, multiplication, and division of complex numbers were developed by the Italian mathematician Raffaele Bombelli. A more abstract formalism for the complex numbers was further developed by the Irish mathematician William Rowan Hamilton, who extended this abstraction to the theory of quaternions. Relations and operations. Equality. Two complex numbers are equal if and only if both their real and imaginary parts are equal. That is, complex numbers z 1 display style z_1 and z 2 display style z underscore 2 are equal if and only if re z 1 equals re z 2 display style operator name re z underscore 1 equals operator name re z underscore 2 and I'm z 1 equals I'm z 2 display style operator name I'm z underscore 1 equals operator name I'm z underscore 2. If the complex numbers are written in polar form, they are equal if and only if they have the same argument and the same magnitude. Topic: Ordering. Since complex numbers are naturally thought of as existing on a two-dimensional plane, there is no natural linear ordering on the set of complex numbers. In fact, there is no linear ordering on the complex numbers that is compatible with addition and multiplication. The complex numbers cannot have the structure of an ordered field. This is because any square in an ordered field is at least 0, but I2 equals -1 equals. Topic: Conjugate. Equals. The complex conjugate of the complex number z equals x plus y is given by x minus y. It is denoted by either z display style overline z or z asterisk. This unary operation on complex numbers cannot be expressed by applying only their basic operations addition, subtraction, multiplication and division. Geometrically, z display style overline z is the reflection of z about the real axis. Conjugating twice gives the original complex number z equals z display style overline z equals z, which makes this operation an involution. The reflection leaves both the real part and the magnitude of z display style z unchanged, that is re z equals re z display style operator name re overline z equals operator name re z quad and z equals z display style quad overline z equals z. The imaginary part and the argument of a complex number z display style z change their sign under conjugation. I'm z equals minus I'm z display style operator name I'm overline z equals operator name I'm z quad and arg z minus arg z mod 2 pi display style quad operator name arg overline z equiv operator name arg z pmod 2 pi. For details on argument and magnitude, see the section on polar form. The product of a complex number z equals x plus y I display style z equals x plus y, and its conjugate is always a positive real number and equals the square of the magnitude of each z equals x 2 plus y 2 equals z 2 equals z 2 display style z cdot overline z equals x caret 2 plus y caret 2 equals z caret 2 equals overline z caret 2. This property can be used to convert a fraction with a complex denominator to an equivalent fraction with a real denominator by expanding both numerator and denominator of the fraction by the conjugate of the given denominator. This process is sometimes called rationalization. of the denominator, although the denominator in the final expression might be an irrational real number, because it resembles the method to remove roots from simple expressions in a denominator. The real and imaginary parts of a complex number z can be extracted using the conjugation re z equals z plus z 2. Display style operator name re z equals dfrac z plus overline z 2 quad and I'm z equals z minus z 2 I. Display style quad operator name I'm z equals dfrac z overline z 2 I. Moreover, a complex number is real if and only if it equals its own conjugate. Conjugation distributes over the basic complex arithmetic operations z plus or minus w equals z plus or minus w. Display style overline z pmw equals overline z pm overline w z w equals z w z w equals z w. Display style overline z c dot w equals overline z c dot overline w quad overline z w equals overline z overline w. Conjugation is also employed in inversive geometry, a branch of geometry studying reflections more general than ones about a line. In the network analysis of electrical circuits, the complex conjugate is used in finding the equivalent impedance when the maximum power transfer theorem is looked for. Addition and subtraction. Two complex numbers a _a and b _b are most easily added by separately adding their real and imaginary parts of the summons. That is to say, a plus b equals x plus y I plus u plus v I equals x plus u plus y plus v I. Display style a plus b equals x plus y plus u plus v I equals x plus u plus y plus v I. Similarly, subtraction can be performed as a minus b equals x plus y I minus u plus v I equals x minus u plus y minus v I. Display style a b equals x plus y u plus v I equals x u plus y v I. Using the visualization of complex numbers in the complex plane, the addition has the following geometric interpretation: the sum of two complex numbers a display style a and b display style b, interpreted as points in the complex plane, is the point obtained by building a parallelogram from the three vertices o display style o and the points of the arrows labeled a display style a and b display style b, provided that they are not on a line. Equivalently, calling these points a b display style a b respectively, and the fourth point of the parallelogram x display style x. The triangles o a b display style oab and x b a display style x b a are congruent. A visualization of the subtraction can be achieved by considering addition of the negative subtrahend. Topic: Multiplication. Since the real part, the imaginary part, and the indeterminate I in a complex number are all considered as numbers in themselves, two complex numbers, given as z equals x plus y I display style z equals x plus y and w equals u plus v I display style w equals u plus v I are multiplied under the rules of the distributive property, the commutative properties, and the defining property I 2 equals minus 1 display style I caret 2 equals minus 1 in the following way: z w equals x plus y I u plus v I equals x u plus v I plus y I u plus v I by the right distributive law equals x u plus x v I plus y I u plus y I v I by the left distributive law equals x u plus y I v I plus x v I plus y I u by the commutativity of addition equals x u plus y v I 2 plus x v I plus y u I by the commutativity of multiplication equals x u plus y v I 2 plus xvi plus yui by the associativity of addition equals xu minus yv plus xvi plus yui by the defining property of I equals xu minus yv plus xv plus yu I by the distributive law. Display style begin aligned z c dot w and equals x plus y c dot u plus vi and n equals x u plus vi plus y u plus vi and n text by the right distributive law and equals shu plus xvi plus u plus yiv and n text by the left distributive law and equals shu plus yiv plus xvi plus u and n text by the commutativity of addition and equals shu plus yv caret 2 plus xvi plus ue and n text by the commutativity of multiplication and equals shu plus yv caret 2 plus xvi plus ue and n text by the associativity of addition and equals shu yv plus xvi plus ue and n text by the defining property of I and equals shu yv plus xv plus yu I and n text by the distributive law. End aligned. Topic: Reciprocal and division. Using the conjugation, the reciprocal of a non-zero complex number z equals x plus y can always be broken down to 1 z equals z z z equals z z 2 equals z x 2 plus y 2 equals x x 2 plus y 2 minus y x 2 plus y 2 I display style frac 1 z equals frac overline z overline z equals frac overline z caret 2 equals frac overline z x caret 2 plus y caret 2 equals frac x caret 2 plus y caret 2 frac y x caret 2 plus y caret 2 I. Since non-zero implies that x 2 plus y 2 display style x caret 2 plus y caret 2 is greater than 0. This can be used to express a division of an arbitrary complex number w equals u plus v I display style w equals u plus vi by a non-zero complex number z display style z as w z equals w 1 z equals u plus v I x x 2 plus y 2 minus y x 2 plus y 2 I equals 1 x 2 plus y 2 u x plus v y plus v x minus u y I display style frac w z equals w c dot frac 1 z equals u plus vi c dot left frac x x caret 2 plus y caret 2 frac y x caret 2 plus y caret 2 I right equals frac 1 x caret 2 plus y caret 2 left ux plus v plus vx uy I right. Topic: Multiplication and division in polar form. Formulas for multiplication, division and exponentiation are simpler in polar form than the corresponding formulas in Cartesian coordinates. Given two complex numbers z1 topic: r1 cos phi 1 plus I sin phi 1 and z2 r2 cos phi 2 plus I sin phi 2 because of the trigonometric identities cos a cos b minus sin a sin b equals cos a plus b display style cos a cos b sin a sin b equals cos a plus b cos a sin b plus sin a cos b equals sin a plus b display style cos a sin b plus sin a cos b equals sin a plus b. We may derive z 1 z 2 equals r 1 r 2 cos phi 1 plus phi 2 plus I sin phi 1 plus phi 2. Display style z underscore 1 z underscore 2 equals r underscore 1 r underscore 2 cos var phi underscore 1 plus var phi underscore 2 plus I sin var phi underscore 1 plus var phi underscore 2. In other words, the absolute values are multiplied and the arguments are added to yield the polar form of the product. For example, multiplying by I corresponds to a quarter turn counterclockwise, which gives back I2 equals -1. The picture at the right illustrates the multiplication of 2 plus I 3 plus I equals 5 plus 5 I. Display style 2 plus I 3 plus I equals 5 plus 5 I. Since the real and imaginary part of 5 plus 5i are equal, the argument of that number is 45 degrees, or pi 4 in radian. On the other hand, it is also the sum of the angles at the origin of the red and blue triangles are arctan 1/3 and arctan 1/2, respectively. Thus, the formula pi 4 equals arctan 1 2 plus arctan 1 3. Display style frac pi 4 equals arctan left frac 1 2 right plus arctan left frac 1 3 right holds. As the arctan function can be approximated highly efficiently, formulas like this, known as Machen-like formulas, are used for high-precision approximations of pi. Similarly, division is given by z 1 z 2 equals r 1 r 2 cos phi 1 minus phi 2 plus I sin phi 1 minus phi 2. Display style frac z underscore 1 z underscore 2 equals frac r underscore 1 r underscore 2 left cos var phi underscore 1 var phi underscore 2 plus I sin var phi underscore 1 var phi underscore 2 right. Topic square root. The square roots of a plus by with b does not equal 0 are plus or minus gamma plus delta I display style pm gamma plus delta I, where gamma equals a plus a 2 plus b 2 2. Display style gamma equals sqrt frac a plus sqrt a caret 2 plus b caret 2 2, and delta equals sgn b minus a plus a 2 plus b 2 2. Display style delta equals operator name sgn b sqrt frac a plus sqrt a caret 2 plus b caret 2 2, where sgn is the signum function. This can be seen by squaring plus or minus gamma plus delta I display style pm gamma plus delta I to obtain a plus by. Here 2 plus b 2 display style sqrt a caret 2 plus b caret 2 is called the modulus of a plus by, and the square root sign indicates the square root with non-negative real part, called the principal square root. Also a 2 plus b 2 equals z Display style sqrt a caret 2 plus b caret 2 equals sqrt z overline z, where z equals a plus b I. Display style z equals a plus by. Topic: Exponentiation. Euler's formula. Euler's formula states that, for any real number x, e I x equals cos x plus I sin x. Display style e caret x equals cos x plus I sin x, where e is the base of the natural logarithm. This can be proved through induction by observing that I 0 equals 1, I 1 equals I 2 equals minus 1, I 3 equals minus I 4 equals 1, I 5 equals I 6 equals minus 1, I 7 equals minus I. Display style begin aligned I caret 0 and equals 1 quad and I caret 1 and equals I quad and I caret 2 and equals minus 1 quad and I caret 3 and equals I caret 4 and equals 1 quad and I caret 5 and equals I quad and I caret 6 and equals minus 1 quad and I caret 7 and equals I end aligned and so on. And by considering the Taylor series expansions of EIX, cos x and sin x, EIX equals 1 plus IX plus IX 2 2 plus IX 3 3 plus IX 4 4 plus IX 5 5 plus IX 6 6 plus IX 7 7 plus I x 8 8 plus equals 1 plus I x minus x 2 2 minus I x 3 3 plus x 4 4 plus I x 5 5 minus x 6 6 minus I x 7 7 plus x 8 8 plus equals 1 minus x 2 2 plus x 4 4 minus x 6 6 plus x 8 8 minus plus I x minus x 3 3 plus x 5 5 minus x 7 7 plus equals cos x plus I sin x. Display style begin aligned e caret x and equals 1 plus I x plus frac x caret 2 2 plus frac x caret 3 3 plus frac x caret 4 4 plus frac x caret 5 5 plus frac x caret 6 6 plus frac x caret 7 7 plus frac x caret 8 8 plus cdots 8 pt and equals 1 plus I x x frac x caret 2 2 frac x caret 3 3 plus frac x caret 4 4 plus frac x caret 5 5 frac x caret 6 6 frac x caret 7 7 plus frac x caret 8 8 plus c dots 8 pt and equals left 1 frac x caret 2 2 plus frac x caret 4 4 frac x caret 6 6 plus frac x caret 8 8 c dots right plus I left x frac x caret 3 3 plus frac x caret 5 5 frac x caret 7 7 plus c dots right 8 pt and equals cos x plus I sin x end aligned. The rearrangement of terms is justified because each series is absolutely convergent. Natural logarithm. It follows from Euler's formula that, for any complex number z written in polar form, z equals r cos phi plus I sin phi. Display style z equals r cos var phi plus I sin var phi. Where r is a non-negative real number, one possible value for the complex logarithm of z is lane z equals lane r plus phi I. Display style lane z equals lane r plus var phi I. Because cosine and sine are periodic functions, other possible values may be obtained. For example, e I pi equals e 3 I pi equals minus 1. Display style e caret I pi equals e caret 3 I pi equals minus 1. So both I pi display style I pi and 3 I pi display style 3 I pi are two possible values for the natural logarithm of minus 1 display style minus 1. To deal with the existence of more than one possible value for a given input, the complex logarithm may be considered a multi-valued function with lane z equals lane r plus phi plus 2 pi k I k element of z. Display style lane z equals left lane r plus var phi plus 2 pi k I mid k in mathb z right. Alternatively, a branch cut can be used to define a single-valued branch of the complex logarithm. Topic: Integer and fractional exponents. We may use the identity lane a b equals b lane a display style lane left a caret b right equals b lane a to define complex exponentiation, which is likewise multi-valued. Lane z north equals lane r cos phi plus I sin phi north equals n lane r cos phi plus I sin phi equals n lane r plus phi plus k 2 pi I k element of Z equals n lane R plus n phi I plus n k 2 pi I k element of Z display style begin aligned lane Z caret north and equals lane R cos var phi plus I sin var phi caret n and equals n lane R cos var phi plus I sin var phi and equals n lane R plus var phi plus k 2 pi I k in math b Z and equals n lane R plus n var phi I plus n k 2 pi I k in math b Z end aligned when n is an integer. This simplifies to de Moivre's formula Zn equals R cos phi plus I sin phi n equals Rn cos n phi plus I sin n phi. Display style Z caret n equals R cos var phi plus I sin var phi caret n equals R caret n c dot cos n var phi plus I sin n var phi. The nth roots of Z are given by Z n equals R n cos phi plus 2 k pi n plus I sin phi plus 2 k pi n. Display style sqrt n Z equals sqrt n R left cos left frac var phi plus 2 k pi n right plus I sin left frac var phi plus 2 k pi n right right for any integer k satisfying 0 k n minus 1. Here n square root r is the usual positive nth root of the positive real number r. While the nth root of a positive real number r is chosen to be the positive real number c satisfying Cn equals r, there is no natural way of distinguishing one particular complex nth root of a complex number. Therefore, the nth root of z is considered as a multivalued function in Z, as opposed to a usual function f, for which f z is a uniquely defined number. Formulas such as z n equals Z display style sqrt n Z caret n equals Z, which holds for positive real numbers, do in general not hold for complex numbers. Topic: Properties. Topic: Field structure. The set C of complex numbers is a field. Briefly, this means that the following facts hold. First, any two complex numbers can be added and multiplied to yield another complex number. Second, for any complex number z, its additive inverse minus z is also a complex number. And third, every non-zero complex number has a reciprocal complex number. Moreover, these operations satisfy a number of laws, for example the law of commutativity of addition and multiplication for any two complex numbers z1 and z2, z1 plus z2 equals z2 plus z1, displaystyle z_1 plus z_2 equals z_2 plus z_1, z1 z2 equals z2 z1, displaystyle z_1 z_2 equals z_2 z_1. These two laws and the other requirements on a field can be proven by the formulas given above, using the fact that the real numbers themselves form a field. Unlike the reals, C is not an ordered field, that is to say, it is not possible to define a relation Z1. In fact, in any ordered field, the square of any element is necessarily positive, so I2 equals -1 precludes the existence of an ordering on C when the underlying field for a mathematical topic or construct is the field of complex numbers. The topic's name is usually modified to reflect that fact. For example, complex analysis, complex matrix, complex polynomial, and complex Lie algebra. Topic: Solutions of polynomial equations. Given any complex numbers called coefficients a0 and the equation a n z n plus a 1 z plus a 0 equals 0, display style a underscore n z caret n plus dots b plus a underscore 1 z plus a underscore 0 equals 0 has at least one complex solution z, provided that at least one of the higher coefficients a1 and is non-zero. This is the statement of the fundamental theorem of algebra, of Carl Friedrich Gauss and Jean-Laurent d'Alembert. Because of this fact, C is called an algebraically closed field. This property does not hold for the field of rational numbers Q. The polynomial x2-2 does not have a rational root, since square root 2 is not a rational number, nor the real numbers are. The polynomial x2 plus a does not have a real root for a greater than 0, since the square of x is positive for any real number x. There are various proofs of this theorem, either by analytic methods such as Liouville's theorem, or topological ones such as the winding number, or a proof combining Galois theory and the fact that any real polynomial of odd degree has at least one real root. Because of this fact, theorems that hold for any algebraically closed field, apply to C. For example, any non-empty complex square matrix has at least one complex eigenvalue. Algebraic characterization. The field C has the following three properties. First, it has characteristic 0. This means that 1 plus 1 plus 1 does not equal 0 for any number of summands, all of which equal 1. Second, its transcendence degree over Q, the prime field of C, is the cardinality of the continuum. Third, it is algebraically closed, see above. It can be shown that any field having these properties is isomorphic as a field to C. For example, the algebraic closure of QP also satisfies these three properties, so these two fields are isomorphic as fields, but not as topological fields. Also, C is isomorphic to the field of complex Puo series. However, specifying an isomorphism requires the axiom of choice. Another consequence of this algebraic characterization is that C contains many proper subfields that are isomorphic to C. Characterization as a topological field. The preceding characterization of C describes only the algebraic aspects of C, that is to say, the properties of nearness and continuity, which matter in areas such as analysis and topology, are not dealt with. The following description of C as a topological field, that is, a field that is equipped with a topology, which allows the notion of convergence, does take into account the topological properties. C contains a subset P, namely the set of positive real numbers of non-zero elements satisfying the following three conditions. P is closed under addition, multiplication and taking inverses. If x and y are distinct elements of P, then either x minus y or y minus x is in P. If S is any non-empty subset of P, then S plus P equals x plus P for some x in C. Moreover, C has a non-trivial involutive automorphism XX*, namely the complex conjugation, such that XX* is in P for any non-zero x in C. Any field F with these properties can be endowed with a topology by taking the sets B x P equals y P minus y minus x asterisk element of P as a base, where x ranges over the field and P ranges over P. With this topology, F is isomorphic as a topological field to C. The only connected locally compact topological fields are R and C. This gives another characterization of C as a topological field, since C can be distinguished from R because the non-zero complex numbers are connected, while the non-zero real numbers are not. Formal construction. Topic construction as ordered pairs. William Rowan Hamilton introduced the approach to define the set C of complex numbers as the set R2 of ordered pairs A, B of real numbers, in which the following rules for addition and multiplication are imposed: A, B plus C, D equals A plus C, B plus D, A, B, C, D equals AC minus BD, BC plus AD. Display style begin aligned A, B plus C, D and equals A plus C, B plus D, A, B, C dot C, D and equals ACBD, BC plus AD, end aligned. It is then just a matter of notation to express A, B as a plus by. Construction as a quotient field. Though this low-level construction does accurately describe the structure of the complex numbers, the following equivalent definition reveals the algebraic nature of C more immediately. This characterization relies on the notion of fields and polynomials. A field is a set endowed with addition, subtraction, multiplication and division operations that behave as is familiar from, say, rational numbers. For example, the distributive law x plus y z equals x z plus y z. Display style x plus y z equals x z plus y z must hold for any three elements x, y, and z of a field. The set R of real numbers does form a field. A polynomial p x with real coefficients is an expression of the form a n x n plus a 1 x plus a 0. Display style a underscore n x caret n plus dots b plus a underscore 1 x plus a underscore 0, where the a0 and are real numbers. The usual addition and multiplication of polynomials endows the set R x of all such polynomials with a ring structure. This ring is called the polynomial ring over the real numbers. The set of complex numbers is defined as the quotient ring R x, x2 plus 1. This extension field contains two square roots of -1, namely the cosets of x and -x, respectively. The cosets of 1 and x form a basis of R x, x2 plus 1 as a real vector space, which means that each element of the extension field can be uniquely written as a linear combination in these two elements. Equivalently, elements of the extension field can be written as ordered pairs A, B of real numbers. The quotient ring is a field, because x2 plus 1 is irreducible over R, so the ideal it generates is maximal. The formulas for addition and multiplication in the ring R x, modulo the relation x2 equals 1, correspond to the formulas for addition and multiplication of complex numbers defined as ordered pairs. So the two definitions of the field C are isomorphic as fields. Accepting that C is algebraically closed, since it is an algebraic extension of R in this approach, C is therefore the algebraic closure of R. Matrix representation of complex numbers. Complex numbers A plus by can also be represented by 2 times 2 matrices that have the following form: a minus BBA display style begin P matrix A and B and A end P matrix. Here the entries A and B are real numbers. The sum and product of two such matrices is again of this form, and the sum and product of complex numbers corresponds to the sum and product of such matrices, the product being a minus BBA C minus DDC equals a C minus BD minus AD minus BC plus AD minus BD plus AC. Display style begin P matrix A and B and A end P matrix begin P matrix C and D and C end P matrix equals begin P matrix ACBD and add BC plus AD and BD plus AC end P matrix. The geometric description of the multiplication of complex numbers can also be expressed in terms of rotation matrices by using this correspondence between complex numbers and such matrices. Moreover, the square of the absolute value of a complex number expressed as a matrix is equal to the determinant of that matrix. Z 2 equals a minus BBA equals a 2 plus B2. Display style Z caret 2 equals begin V matrix A and B and A end V matrix equals a caret 2 plus B caret 2. The conjugate Z display style overline Z corresponds to the transpose of the matrix. Though this representation of complex numbers with matrices is the most common, many other representations arise from matrices other than 0-110 display style BIGL begin small matrix 0 and -1 1 and 0 end small matrix big R that square to the negative of the identity matrix. See the article on 2 times 2 real matrices for other representations of complex numbers. Topic: Complex analysis. The study of functions of a complex variable is known as complex analysis and has enormous practical use in applied mathematics as well as in other branches of mathematics. Often, the most natural proofs for statements in real analysis or even number theory employ techniques from complex analysis. See prime number theorem for an example. Unlike real functions, which are commonly represented as two-dimensional graphs, complex functions have four-dimensional graphs and may usefully be illustrated by color-coding a three-dimensional graph to suggest four dimensions, or by animating the complex function's dynamic transformation of the complex plane. Complex exponential and related functions. The notions of convergent series and continuous functions in real analysis have natural analogues in complex analysis. A sequence of complex numbers is said to converge if and only if its real and imaginary parts do. This is equivalent to the epsilon delta definition of limits, where the absolute value of real numbers is replaced by the one of complex numbers. From a more abstract point of view, C, endowed with the metric d z 1 z 2 equals z 1 minus z 2. Display style operator name d z underscore 1 z underscore 2 equals z underscore 1 z underscore 2 is a complete metric space, which notably includes the triangle inequality z 1 plus z 2 z 1 plus z 2. Display style z underscore 1 plus z underscore 2 leq z underscore 1 plus z underscore 2 for any two complex numbers z1 and z2. Like in real analysis, this notion of convergence is used to construct a number of elementary functions. The exponential function exp z, also written ez, is defined as the infinite series exp z equals 1 plus z plus z 2 2 1 plus z 3 3 2 1 plus equals n equals 0 infinity z n n. Display style exp z equals 1 plus z plus frac z caret 2 2 c dot 1 plus frac z caret 3 3 c dot 2 c dot 1 plus c dot s equals sum underscore n equals 0 caret inf t frac z caret n n. The series defining the real trigonometric functions sine and cosine, as well as the hyperbolic functions sin and cosh, also carry over to complex arguments without change. For the other trigonometric and hyperbolic functions, such as tangent, things are slightly more complicated, as the defining series do not converge for all complex values. Therefore, one must define them either in terms of sine, cosine and exponential, or, equivalently, by using the method of analytic continuation. Euler's formula states exp I phi equals cos phi plus I sin phi. Display style exp I var phi equals cos var phi plus I sin var phi. For any real number phi, in particular, exp I pi equals minus 1. Display style exp I pi equals minus 1. Unlike in the situation of real numbers, there is an infinitude of complex solutions z of the equation exp z equals w. Display style exp z equals w. For any complex number w does not equal 0. It can be shown that any such solution z, called complex logarithm of w, satisfies log west equals lane W plus I arg W display style log west equals lane W plus I arg W, where arg is the argument defined above and lane the real natural logarithm. As arg is a multivalued function, unique only up to a multiple of 2 pi, log is also multivalued. The principal value of log is often taken by restricting the imaginary part to the interval -pi, pi. Complex exponentiation z omega is defined as z omega equals exp omega log z display style z caret omega equals exp omega log z, and is multi-valued except when omega display style omega is an integer. For omega equals 1 n, for some natural number n, this recovers the non-uniqueness of nth roots mentioned above. Complex numbers, unlike real numbers, do not in general satisfy the unmodified power and logarithm identities, particularly when naively treated as single-valued functions. See failure of power and logarithm identities. For example, they do not satisfy a b c equals a b c display style a caret bc equals left a caret b right caret c. Both sides of the equation are multivalued by the definition of complex exponentiation given here, and the values on the left are a subset of those on the right. Topic: Holomorphic functions. A function f, c(c) is called holomorphic if it satisfies the Cauchy-Riemann equations. For example, any R-linear map c(c) can be written in the form f z equals a z plus b z. Display style f z equals as plus b overline z with complex coefficients a and b. This map is holomorphic if and only if b equals 0. The second summand b z display style b overline z is real differentiable, but does not satisfy the Cauchy-Riemann equations. Complex analysis shows some features not apparent in real analysis. For example, any two holomorphic functions f and g that agree on an arbitrarily small open subset of C necessarily agree everywhere. Meromorphic functions, functions that can locally be written as f z, z-z0 n with a holomorphic function f, still share some of the features of holomorphic functions. Other functions have essential singularities, such as sin 1, z at z equals 0 equals. Topic: Applications. Equals. Complex numbers have essential concrete applications in a variety of scientific and related areas such as signal processing, control theory, electromagnetism, fluid dynamics, quantum mechanics, cartography, and vibration analysis. Some applications of complex numbers are equals. Topic: Control theory. Equals. In control theory, systems are often transformed from the time domain to the frequency domain using the Laplace transform. The system's zeros and poles are then analyzed in the complex plane. The root locus, Nyquist plot, and Nichols plot techniques all make use of the complex plane. In the root locus method, it is important whether zeros and poles are in the left or right half-planes, i.e. have real part greater than or less than 0. If a linear, time-invariant (LTI) system has poles that are in the right half-plane, it will be unstable. All in the left half-plane, it will be stable. On the imaginary axis, it will have marginal stability. If a system has zeros in the right half-plane, it is a nonminimum phase system. Topic: Improper integrals. In applied fields, complex numbers are often used to compute certain real-valued improper integrals, by means of complex-valued functions. Several methods exist to do this, see methods of contour integration. Dynamic equations. In differential equations, it is common to first find all complex roots r of the characteristic equation of a linear differential equation or equation system and then attempt to solve the system in terms of base functions of the form f t. ERT. Likewise, in difference equations, the complex roots r of the characteristic equation of the difference equation system are used, to attempt to solve the system in terms of base functions of the form f t. RT. Signal analysis. Complex numbers are used in signal analysis and other fields for a convenient description for periodically varying signals. For given real functions representing actual physical quantities, often in terms of sines and cosines, corresponding complex functions are considered of which the real parts are the original quantities. For a sine wave of a given frequency, the absolute value, z, of the corresponding z is the amplitude and the argument arg z is the phase. If Fourier analysis is employed to write a given real-valued signal as a sum of periodic functions, these periodic functions are often written as complex-valued functions of the form x t equals re x t. Display style x t equals operator name re x t and x t equals a e I omega t equals a e I phi e I omega t equals a e I omega t plus phi. Display style x t equals a caret I omega t equals a caret I phi e caret I omega t equals a caret I omega t plus phi, where omega represents the angular frequency and the complex number a encodes the phase and amplitude as explained above. This use is also extended into digital signal processing and digital image processing, which utilize digital versions of Fourier analysis and wavelet analysis to transmit, compress, restore, and otherwise process digital audio signals, still images, and video signals. Another example, relevant to the two-side bands of amplitude modulation of AM radio, is cos omega plus alpha t plus cos omega minus alpha t equals re e I omega plus alpha t plus e I omega minus alpha t equals re e I alpha t plus e minus I alpha t e I omega t equals re 2 cos alpha t e I omega t equals 2 cos alpha t re e I omega t equals 2 cos alpha t cos omega t. Display style begin aligned cos omega plus alpha t plus cos left omega alpha t right and equals operator name re left e caret I omega plus alpha t plus e caret I omega alpha t right and equals operator name re left e caret I alpha t plus e caret I alpha t right c dot e caret I omega t right and equals operator name re left 2 cos alpha t c dot e caret I omega t right and equals 2 cos alpha t c dot operator name re left e caret I omega t right and equals 2 cos alpha t c dot cos left omega t right. End aligned. Topic: Geometry. Topic: Shapes. Three non-collinear points u v w display style u v w in the plane determine the shape of the triangle u v w display style u v w. Locating the points in the complex plane, this shape of a triangle may be expressed by complex arithmetic as s u v w equals u minus w u minus v. Display style s u v w equals frac uw uv. The shape s display style s of a triangle will remain the same, when the complex plane is transformed by translation or dilation by an affine transformation, corresponding to the intuitive notion of shape, and describing similarity. Thus each triangle u v w u v w is in a similarity class of triangles with the same shape. Fractal geometry. The Mandelbrot set is a popular example of a fractal formed on the complex plane. It is defined by plotting every location C C where iterating the sequence f c z equals z 2 plus c display style f underscore c z equals z caret 2 plus c does not diverge when iterated infinitely. Similarly, Julia sets have the same rules, except where c display style c remains constant. Topic: Triangles. Every triangle has a unique Steiner inellipse, an ellipse inside the triangle and tangent to the midpoints of the three sides of the triangle. The foci of a triangle's Steiner inellipse can be found as follows. According to Martin's theorem, denote the triangle's vertices in the complex plane as a xa plus yaa b xb plus ybi, and c equals xc plus yci. Write the cubic equation x minus a x minus b x minus c equals 0. Display style script style xa xb xc equals 0. Take its derivative, and equate the quadratic derivative to 0. Martin's theorem says that the solutions of this equation are the complex numbers denoting the locations of the two foci of the Steiner inellipse. Algebraic number theory. As mentioned above, any non-constant polynomial equation in complex coefficients has a solution in C a fortiori. The same is true if the equation has rational coefficients. The roots of such equations are called algebraic numbers. They are a principal object of study in algebraic number theory. Compared to Q, the algebraic closure of Q, which also contains all algebraic numbers, C has the advantage of being easily understandable in geometric terms. In this way, algebraic methods can be used to study geometric questions and vice versa. With algebraic methods, more specifically applying the machinery of field theory to the number field containing roots of unity, it can be shown that it is not possible to construct a regular nonagon using only compass and straightedge, a purely geometric problem. Another example are Gaussian integers, that is, numbers of the form x plus iy, where x and y are integers, which can be used to classify sums of squares. Analytic number theory. Analytic number theory studies numbers, often integers or rationals, by taking advantage of the fact that they can be regarded as complex numbers, in which analytic methods can be used. This is done by encoding number-theoretic information in complex-valued functions. For example, the Riemann zeta function zeta s is related to the distribution of prime numbers. In physics. Electromagnetism and electrical engineering. In electrical engineering, the Fourier transform is used to analyze varying voltages and currents. The treatment of resistors, capacitors, and inductors can then be unified by introducing imaginary, frequency-dependent resistances for the latter two and combining all three in a single complex number called the impedance. This approach is called phasor calculus. In electrical engineering, the imaginary unit is denoted by J, to avoid confusion with I, which is generally in use to denote electric current, or, more particularly, I, which is generally in use to denote instantaneous electric current. Since the voltage in an AC circuit is oscillating, it can be represented as V T equals V 0 E J omega T equals V 0 cos omega T plus J sin omega T. Display style V T equals V underscore 0 E caret J omega T equals V underscore 0 left cos omega T plus J sin omega T right. To obtain the measurable quantity, the real part is taken. V T equals R E V equals R E V 0 E J omega T equals V 0 cos omega T. Display style V T equals mathrm re V equals mathrm re left V underscore 0 E caret J omega T right equals V underscore 0 cos omega T. The complex valued signal V T display style V T is called the analytic representation of the real valued measurable signal V T display style V T. Topic: Fluid dynamics. In fluid dynamics, complex functions are used to describe potential flow in two dimensions. Topic: Quantum mechanics. The complex number field is intrinsic to the mathematical formulations of quantum mechanics, where complex Hilbert spaces provide the context for one such formulation that is convenient and perhaps most standard. The original foundation formulas of quantum mechanics, the Schrödinger equation and Heisenberg's matrix mechanics, make use of complex numbers. Relativity. In special and general relativity, some formulas for the metric on spacetime become simpler if one takes the time component of the spacetime continuum to be imaginary. This approach is no longer standard in classical relativity, but is used in an essential way in quantum field theory. Complex numbers are essential to spinors, which are a generalization of the tensors used in relativity. Topic: History. The earliest fleeting reference to square roots of negative numbers can perhaps be said to occur in the work of the Greek mathematician Hero of Alexandria in the 1st century AD, where in his Stereometrica he considers, apparently in error, the volume of an impossible frustum of a pyramid to arrive at the term 81 minus 144 equals 3 I 7. Display style sqrt 81 to 144 equals 3 I sqrt 7. In his calculations, although negative quantities were not conceived of in Hellenistic mathematics and Heron merely replaced it by its positive 144 minus 81 equals 3 7. Display style sqrt 144 to 81 equals 3 sqrt 7. The impetus to study complex numbers as a topic in itself first arose in the 16th century when algebraic solutions for the roots of cubic and quartic polynomials were discovered by Italian mathematicians. See Niccolò Fontana Tartaglia, Gerolamo Cardano. It was soon realized that these formulas, even if one was only interested in real solutions, sometimes required the manipulation of square roots of negative numbers. As an example, Tartaglia's formula for a cubic equation of the form x 3 equals p x plus q display style x caret 3 equals px plus q gives the solution to the equation x3 equals x as 1 3 minus 1 1 3 plus minus 1 minus 1 3 display style tfrac 1 sqrt 3 left sqrt minus 1 right caret 1/3 plus left sqrt minus 1 right caret minus 1/3 right. At first glance this looks like nonsense. However, formal calculations with complex numbers show that the equation z3 equals I has solutions minus I 3 2 plus 1 2 I display style tfrac sqrt 3 2 plus tfrac 1 2 I and minus 3 2 plus 1 2 I display style tfrac sqrt 3 2 plus tfrac 1 2 I. Substituting these in turn for minus 1 1 3 display style sqrt minus 1 caret 1/3 in Tartaglia's cubic formula and simplifying, one gets 0, 1 and minus 1 as the solutions of x3 minus x equals 0. Of course this particular equation can be solved at sight, but it does illustrate that when general formulas are used to solve cubic equations with real roots, then, as later mathematicians showed rigorously, the use of complex numbers is unavoidable. Raphael Bombelli was the first to explicitly address these seemingly paradoxical solutions of cubic equations and developed the rules for complex arithmetic trying to resolve these issues. The term, imaginary, for these quantities was coined by René Descartes in 1637, although he was at pains to stress their imaginary nature. Sometimes only imaginary, that is, one can imagine as many as I said in each equation, but sometimes there exists no quantity that matches that which we imagine. Quelquefois seulement imaginaires c'est à dire que l'on peut toujours en imaginer autant que j'ai dit en chaque occasion, mais qu'il n'y a quelquefois aucune quantité qui corresponde à celle qu'on imagine. A further source of confusion was that the equation minus 1 2 equals minus 1 minus 1 equals minus 1. Display style sqrt minus 1 caret 2 equals sqrt minus 1 sqrt minus 1 equals minus 1 seem to be capriciously inconsistent with the algebraic identity a b equals a b. Display style sqrt sqrt b equals sqrt ab, which is valid for non-negative real numbers a and b, and which was also used in complex number calculations with one of a, b positive and the other negative. The incorrect use of this identity and the related identity 1 a equals 1 a. Display style tfrac 1 sqrt a equals sqrt tfrac 1 a. In the case when both a and b are negative, even bedeviled Euler. This difficulty eventually led to the convention of using the special symbol I in place of square root minus 1 to guard against this mistake. Even so, Euler considered it natural to introduce students to complex numbers much earlier than we do today. In his elementary algebra textbook, Elements of Algebra, he introduces these numbers almost at once and then uses them in a natural way throughout. In the 18th century, complex numbers gained wider use, as it was noticed that formal manipulation of complex expressions could be used to simplify calculations involving trigonometric functions. For instance, in 1730 Abraham de Moivre noted that the complicated identities relating trigonometric functions of an integer multiple of an angle to powers of trigonometric functions of that angle could be simply re-expressed by the following well-known formula, which bears his name, de Moivre's formula. Cos theta plus I sin theta n equals cos n theta plus I sin n theta. Display style cos theta plus I sin theta caret n equals cos n theta plus I sin n theta. In 1748 Leonhard Euler went further and obtained Euler's formula of complex analysis. Cos theta plus I sin theta equals e I theta. Display style cos theta plus I sin theta equals e caret I theta. By formally manipulating complex power series and observed that this formula could be used to reduce any trigonometric identity to much simpler exponential identities. The idea of a complex number as a point in the complex plane above was first described by Caspar Wessel in 1799, although it had been anticipated as early as 1685 in Wallace's De Algebra Tractatus. Wessel's memoir appeared in the Proceedings of the Copenhagen Academy but went largely unnoticed. In 1806 Jean-Robert Argand independently issued a pamphlet on complex numbers and provided a rigorous proof of the fundamental theorem of algebra. Carl Friedrich Gauss had earlier published an essentially topological proof of the theorem in 1797 but expressed his doubts at the time about the true metaphysics of the square root of -1. It was not until 1831 that he overcame these doubts and published his treatise on complex numbers as points in the plane, largely establishing modern notation and terminology. In the beginning of the 19th century, other mathematicians discovered independently the geometrical representation of the complex numbers: Bouet, Maury, Warren, Francais and his brother, Belovitis. The English mathematician G.H. Hardy remarked that Gauss was the first mathematician to use complex numbers in a really confident and scientific way, although mathematicians such as Niels Henrik Abel and Carl Gustav Jacob Jacobi were necessarily using them routinely before Gauss published his 1831 treatise. Augustin Louis Cauchy and Bernhard Riemann together brought the fundamental ideas of complex analysis to a high state of completion, commencing around 1825 in Cauchy's case. The common terms used in the theory are chiefly due to the founders. Argand called cos phi plus I sin phi. display style cos phi plus I sin phi. The direction factor and r equals a 2 plus b 2. Display style r equals sqrt a caret 2 plus b caret 2. The modulus, Cauchy 1828 called cos phi plus I sin phi. Display style cos phi plus I sin phi. The reduced form l'expression réduite and apparently introduced the term argument. Gauss used I for minus 1. Display style sqrt minus 1. Introduced the term complex number for a plus by and called a2 plus b2 the norm. The expression direction coefficient, often used for cos phi plus I sin phi. Display style cos phi plus I sin phi is due to Hankel 1867, and absolute value for modulus is due to Weierstrass. Later classical writers on the general theory include Richard Dedekind, Otto Holder, Felix Klein, Henri Poincaré, Hermann Schwarz, Karl Weierstrass and many others. Generalizations and related notions. The process of extending the field R of reals to C is known as the Cayley-Dickson construction. It can be carried further to higher dimensions, yielding the quaternions H and octonions O which as a real vector space are of dimension 4 and 8, respectively. In this context the complex numbers have been called the binarions, just as by applying the construction to reals the property of ordering is lost. Properties familiar from real and complex numbers vanish with each extension. The quaternions lose commutativity, i.e., x y does not equal y x for some quaternions x, y, and the multiplication of octonions, additionally to not being commutative, fails to be associative, x y z does not equal x y z for some octonions x, y, z. Reals, complex numbers, quaternions and octonions are all normed division algebras over R by Hurwitz's theorem. They are the only ones. The Sedenions, the next step in the Cayley-Dickson construction, fail to have this structure. The Cayley-Dickson construction is closely related to the regular representation of C, thought of as an R algebra, an R vector space with a multiplication with respect to the basis 1, I. This means the following: the R linear map CC ZWZ displaystyle mathb C right arrow mathb C Z mapsto WZ for some fixed complex number W can be represented by a 2 times 2 matrix once a basis has been chosen. With respect to the basis 1, I, this matrix is re W minus I'm W I'm W re W displaystyle begin P matrix operatorname re W and operatorname I'm W operatorname I'm W and operatorname re W end P matrix, i.e., the one mentioned in the section on matrix representation of complex numbers above. While this is a linear representation of C in the 2 times 2 real matrices, it is not the only one. Any matrix J equals PQR minus P, P2 plus QR plus 1 equals 0. Display style J equals begin P matrix P and Q R and P end P matrix quad P caret 2 plus QR plus 1 equals 0 has the property that its square is the negative of the identity matrix J2 equals minus I. Then Z equals AI plus BJ, A, B element of R display style Z equals I plus BJ, A, B in Math BF R is also isomorphic to the field C, and gives an alternative complex structure on R2. This is generalized by the notion of a linear complex structure. Hypercomplex numbers also generalize R, C, H, and O. For example, this notion contains the split complex numbers, which are elements of the ring R x, x2-1 as opposed to R x, x2 plus 1. In this ring, the equation A2 equals 1 has 4 solutions. The field R is the completion of Q, the field of rational numbers, with respect to the usual absolute value metric. Other choices of metrics on Q lead to the fields Qp of p-adic numbers for any prime number p, which are thereby analogous to R. There are no other non-trivial ways of completing Q than R and Qp, by Ostrowski's theorem. The algebraic closures Q p overline math BF Q underscore p of Qp still carry a norm, but unlike C are not complete with respect to it. The completion C P display style math C underscore P of Q P display style overline math Q underscore P turns out to be algebraically closed. This field is called p-adic complex numbers by analogy. The fields R and Qp and their finite field extensions, including C, are local fields. See also: Algebraic surface, circular motion using complex numbers, complex base system, complex geometry, complex square root, Eisenstein integer, Euler's identity, Gaussian integer, Riemann sphere extended complex plane, root of unity, unit complex number. Notes